Hello students, in the previous video we have discussed energy levels of hydrogen atom. It means the hydrogen spectrum consists of different types of series. Each series contains different wavelengths. So what is the speciality of each series? It is a notable point. For each series there is a transition of electron from outer orbit to fixed inner orbit. For Lyman series there are number of transitions, but each transition is from different outer orbit to fixed inner orbit. The inner orbit is first orbit. So for a different series, inner orbit is fixed. For different series, inner orbit is fixed. You have to remember the inner orbit number for each series. For Balmer series, it is 2 second orbit. For Paschen, it is 3. For bracket series, it is 4. For fund series, it is 5. So you have to remember this inner orbit number for each series. So when the transition takes place, when the electron goes to the outer orbit and there it becomes unstable. Suppose the electron is in the first orbit in case of hydrogen atom. So this is the first orbit. When it absorbs some energy, it goes to outer orbit. And outer orbits are nothing but excited states of the electron. When the electron goes to suppose second orbit, this is the first excited state. First excited state means when electron receives some energy. For example, if the electron is jumped from first orbit to second orbit, it should absorb the energy 10.2 electron volt. Then it will go to the second orbit. So now the electron is in the excited state. This is the first excited state. So to go to excited state, the electron should absorb some energy. Electron has to absorb some energy, then it will go to the outer orbit. The energy which is absorbed by electron and excited state depends on this absorbed energy. Suppose the electron absorbs 12.09 electron volt energy, then it will go to or jump to the next orbit, that is n is equal to 3, and we call this orbit as second excited state. So second excited state, the energy absorbed by the electron is different. Now the electron in the first orbits absorb the energy and goes into outer orbit depending on absorbed energy. And what the orbit is called, the energy is, that orbit is called excited orbit or excited level, excited state, and the energy required to take the electron from ground state is n is equal to 1, first orbit, to an excited state is called excitation energy. Means just we have seen 10.2 electron volt is the excitation energy of which orbit? N is equal to 2. The electron jumps to second orbit or second energy level. The minimum excitation energy is the energy required to take electron from ground state to first excited state. First excited state means principal quantum number is n is equal to 2. So this is the minimum excitation energy because the orbit is second orbit next to first ground state. So from ground state the electron goes to the second orbit, that is the first excited state, by absorbing energy equal to 10.2 electron volt. So this type of energy is absorbed by the electron and then goes to excited state. But excited state is unstable state. The electron cannot revolve in the excited state. So it returns to the ground state in one or two steps. So what is the excitation energy? Excitation energy of any state is the difference between energies of the that excited state or that orbit and the ground state. Excitation energy you can calculate by this formula. Minimum excitation energy E2 minus E1. Then excitation energy of third orbit, it is E3 minus E1. So electron absorbs energy and goes to excited state. That state depends on absorbed energy, and you can find the excitation energy by taking difference between two energies, energy of that orbit and energy of the ground orbit or ground state. Next part is ionization energy or binding energy. What is meant by binding energy? This definition is similar to binding energy of an object in gravitational field. This you had studied in 11th standard. So what is ionization or binding energy? This definition is asked for 1 mark in the board exam. The minimum energy required, it is a minimum energy required to remove electron in the ground state so as to set it free from the atom is called ionization energy. It is also called binding energy of hydrogen atom, because in case of hydrogen atom the electron is in the first orbit. This is a nucleus, positively charged nucleus, and this is first orbit. So when the electron jumps to the second orbit, this electron is bound to the atom or bound to the nucleus. The electron is in the field of nucleus. When the electron jumps from its ground state to higher, almost highest energy state, or E is equal to 0 energy state, that is n is equal to infinity. Orbit number is n is equal to infinity. Here, when the energy of electron in this orbit, infinite orbit, is 0, means this electron is not bound to the nucleus. The electron is free from the nucleus field. So how much energy should supply to this electron to free from its nucleus field? Obviously it is 13.6 electron volt, because energy of electron in the ground state is minus 13.6 electron volt. When the electron absorbs 13.6 electron volt, it will jump to the infinite distance. It will jump to the orbit number infinity, where the energy is 0. The field of nucleus is no longer exist at this position. So electron is free from the atom, free from the atom. So this is the minimum energy. Minimum, it is a minimum energy. At least the electron should absorb 13.6 electron volt to free from nucleus field. At least this is the least energy. Least energy required to set the electron free from the atom. So this is a binding energy. So binding energy of hydrogen atom is 13.6 electron volt. You may remember this by giving plus sign, because the total energy is minus in the first state, that is in the ground state where n is equal to 1, minus 13.6 electron volt Then actual the formula was binding energy is equal to minus total energy. So this is minus minus becomes plus, so it is 13.6 electron volt for hydrogen atom. So the definition is asked for 1 mark. Now Rydberg's formula. We have discussed that when there is a transition of electron from outer orbit to fixed inner orbit, so this is positively charged nucleus, this is the first orbit, second, third, fourth. If the electron is in the fourth orbit, in case of hydrogen atom, then this electron is not stable. It returns to its ground state by emitting radiation in terms of photon. Photon is a light particle by emitting radiations. Now this radiation appeared as a spectral line in the spectrum. So spectral line in the spectrum has a definite wavelength lambda. And how this is determined? What is the wavelength of this spectral line? So it is given by Balmer's empirical formula, which we have discussed in the previous video. 1 by lambda is equal to r into bracket 1 upon n square minus 1 by m square. What is n? N is a number of inner orbit and m is a number of outer orbit. From these two values and the constant r, which is given by Balmer, you can find lambda. Lambda, that is wavelength of the radiation or wavelength of the photon. So here the same formula is derived by Rydberg's and called Rydberg's formula. So Rydberg's formula is similar to Balmer's empirical formula. This formula is given by Balmer. According to Bohr's third postulate, the energy is emitted by the electron during the transition of electron from outer orbit to inner orbit. Always there is an emission of spectral line, emission of photon when there is a transition from outer to inner orbit. So the spectral lines or this spectrum is called emission spectrum. And when the electron absorbs energy and goes to outer orbit, the spectrum is called absorption spectrum. So here we are dealing with only emission spectrum. The energy emitted in the form of photon. The energy of photon is h nu. Nu is the frequency and nu is given by this formula. Nu is equal to c by lambda. Nu is frequency, the symbol frequency is nu. So nu is equal to c upon lambda, where c is the velocity of light in vacuum and lambda is the wavelength. So this is the relation we know. Now we have to derive the Rydberg's formula. Rydberg formula derivation is asked for 2 or 3 marks in the exam, board exam. To derive the formula, first we have to write the equation of Bohr's third postulate. The energy difference between two orbits, Em minus En is equal to h nu. This is the equation of Bohr's third postulate. M is greater than N because outer orbit has greater energy than inner orbit. So put the expressions for energies by considering mth orbit and nth orbit. So here h nu is equal to energy is negative minus me z square e raised to 4 upon 8 epsilon 0 square h square. Here the orbit number is m, so put here m square instead of n square, minus again the expression for total energy. So minus minus m e z square e raised to 4 upon 8 epsilon 0 square h square n square. This is for mth orbit, this is for nth orbit. So take the common. So this minus and this minus becomes plus. So this is the nth orbit term is positive. So we'll write the next step. This is equation number 2. Common term m e z square e raised to 4 8 epsilon 0 square h square. In bracket the nth term is positive. So 1 by n square, and this mth term is negative 1 by m square. Now the next step, the Rydberg formula deals with the wavelength of spectral line. So you have to derive the formula for wavelength. Hc by lambda. How it is Hc by lambda? Just we have seen the relation E is equal to h nu. E is equal to h nu. So nu is equal to c by lambda. So E is equal to h nu hc by lambda. So other is the part of remaining is same. So 1 by lambda, transfer this h and c to the right side in the denominator. So the term becomes here h square and one more h is there, so it is h cube and c is there. So 1 by n square minus 1 by m square. So this is equation number 3. Now here me, mass of electron, e raised to 4, charge on electron raised to 4, epsilon 0 square, 8 is number, h is a Planck's constant, c is velocity of light. So these are the constant terms. Only z is different. It is different for different atoms. If there is a hydrogen atom, then z is equal to 1. But for other atoms, z is different. So you can write the constant term RH, then z square, 1 upon n square minus 1 by m square. This is RH is constant given by me e raised to 4 upon this term. And what RH is called? Obviously it is Rydberg's constant. What is the value of this? By substituting all these values which are fixed, mass of electron, charge, then epsilon 0, h and c, RH is equal to 1.097 into 10 raised to 7 meter inverse. So this is similar to the empirical value given by Balmer. So equation 4 is called Rydberg's formula, and this Rydberg's formula explains different series observed in hydrogen spectrum. So what are the series? Take the two examples. Lyman series, transition of electron from outer orbit to fixed first inner orbit. The orbit number is n is equal to 1. The transition from all outer different orbits to fixed inner orbit, n is equal to 1. The series is Lyman series. So you can write the formula for Lyman series also. 1 by lambda, RH constant, Z is equal to 1 for hydrogen atom, 1 by 1 square. This n is equal to 1, so 1 square minus 1 by m square, and m can take the outer orbits 2, 3, 4 immediately higher to the inner orbit 2, 3, 4, 5 etc. up to infinity. So next is suppose Balmer series. The inner orbit number is 2, outer orbit 3, 4, 5 etc. And the formula becomes 1 by lambda is equal to RH, 1 upon 2 square. Here you can write 4 minus 1 by m square. So these are the wavelength of Lyman series. Put the value of m and you will get the definite wavelength in the each series. Suppose if you want to find out wavelength of Lyman series, wavelength of third line, wavelength of third line in Lyman series, the numerical is asked in this way: obtain wavelength of third line in Lyman series. So which is the third line? From 2 to 1, it is the first line. Second line is from 3 to 1, and third line is from 4 to 1. Then here you have to put m is equal to 4 and find the wavelength. In such examples, RH is given to you 1.097 into 10 raised to 7 meter inverse. But mostly we require this 1 by RH, because here the left hand side is not lambda, it is 1 by lambda. So we always require this type of value, and this is equal to, in Armstrong, this is almost equal to 911 Armstrong, or you can take this value like this or like this also, but these are in Armstrong, and 1 Armstrong is equal to 10 raised to minus 10 meter. So this type of value is required. RH is given to you. If you take such type of values 911 up to 912, then quickly you can solve the numerical. Suppose there is one tricky numericals which are asked in the exam as well as in the multiple choice. Find shortest and longest wavelength in, suppose, Lyman series. The same theory can be applied to the other series also. We will take only just Lyman series. So Lyman series, the transition is towards first orbit from outer orbit. So last one is n is equal to infinity. Here n is equal to 2 and so on. So there is a first transition, first wavelength, then this is a second transition, and this is a last transition. This last transition is also called series limit. So which transition, which radiation or which photon has shortest wavelength and which photon has longest wavelength? We'll consider the boundaries of Lyman series. Series limit, here again the photon is emitted. Which photon has greater energy? Which photon has greater energy? From 2 to 1 or from infinity to 1? Which photon has greater energy? Obviously, the series limit line, this last line, the photon has greater energy. How can you find the energy? Here energy of this state is 0 and energy of first orbit is minus 13.6 electron volt. So the energy of emitted photon is the difference between two energies. So 0 minus 13.6, it is a 13.6. The energy of this photon is 13.6 electron volt, and for this photon what is the energy? The energy is 10.2 electron volt. Take the difference between these two. N is equal to 2, what is the energy, and n is equal to 1, what is the energy, then take the difference. This will be the energy of photon. So which photon has greater energy? The transition, when there is a transition from n equal to infinity to n equal to 1. If the photon has greater energy frequency is greater, the frequency of that radiation is greater, energy greater, frequency greater, but wavelength is smallest, because this is the relation, E is equal to h nu h c by lambda. So if energy is greater, wavelength is smaller. So smallest, it is the greatest energy. From n equal to infinity to n equal to 1, the emitted photon has greatest energy. In this Lyman series, we are dealing only with the Lyman series. The same situation is applied to another series. So smallest wavelength is there is a transition from, when there is a transition from n equal to infinity to n equal to 1, and from n equal to 2 to n equal to 1, this is the longest wavelength. This is the longest wavelength, and series limit as the shortest wavelength. So when the, if you draw this long line, then wavelength is short. Draw the small line. This is a small line. You can remember in this way also, small line. The energy is small, but the wavelength is largest. Actually, this is the relation. Hc by lambda. Energy greater, lambda is small. So what will be the formula? 1 by lambda is equal to, when this is shortest, the formula becomes Rydberg's constant RH 1 upon 1 square, this is fixed orbit, minus 1 upon shortest. Shortest means n is equal to infinity. N is equal to infinity square. So this is RH by 1, and lambda for shortest is equal to 1 by RH. So again we require this type of, so this is 911 Armstrong, or 911 into 10 raised to minus 10 meter. This is approximately 911 Armstrong. So for longest, here instead of infinity we have to take number 2 for longest. For longest, equal to RH 1 by 1 square minus 1 by 2 square. So this becomes RH 1 minus 1 by 4, and solve this, you will get longest wavelength in the Lyman series. Wavelength long, frequency is high, and so such type of series occur in ultraviolet region. So in this way you can calculate shortest and longest wavelength in different series. Longest wavelength, outer orbit is n equal to infinity and inner orbit is fixed. For a series, inner orbit is fixed, and for longest, take the outer orbit immediate to the inner orbit and put the value in the formula and obtain wavelength of longest wavelength of the series. Next we will consider some points regarding with NCRT viewpoints. So these points you have to remember for competitive exams just like NEET and JEE. First is distance of closest approach. Closest approach distance means, see here, when when alpha particle is incident on atom, it is normally incident on atom. In atom there is a positively charged nucleus at the center, and suppose alpha particle is emitted from the source. Alpha particle is emitted from the source with certain maximum kinetic energy. When this alpha particle is tracing this path, it comes closer to the nucleus, but it does not incident on the nucleus. It returns back from some distance. It does not collide with the nucleus. Because nucleus is positively charged, alpha particle is also positively charged. So there is a large repulsive force at some distance, because there is a repulsive force between positively charged particle and positively charged nucleus. So when this alpha particles comes in the field of nucleus, the nucleus exerts force on the alpha particle. So there is a greater repulsive force at some distance. Due to this repulsive force, the velocity of alpha particles becomes zero and it returns back in the reverse direction. So this distance between center of positively charged nucleus and the alpha particle from its returning position where it returns, this distance is known as distance of closest approach. Suppose alpha particle coming from source, having maximum kinetic energy, then this distance becomes small, because due to maximum kinetic energy it reaches near the nucleus. So this distance is not constant, it depends on the kinetic energy. Initial kinetic energy which is given to the alpha particle, the distance d depends on that kinetic energy. So you know that Z is equal to 79 for gold, because in the Rutherford's experiment the gold foil is used. What is the distance of closest approach? Distance between center of alpha particle and center of nucleus where alpha returns. Center of alpha particles means this is alpha particle, center of alpha particle and center of nucleus. So alpha particle comes here and returns. So this is the position, and from this point you have to measure the distance. So d is the distance of closest approach. So to find the formula for d, here the conservation of conservation of energy, mechanical energy is used. Kinetic energy of alpha particle is converted into potential energy of alpha particle, where the V is 0 means kinetic energy becomes 0, then it is converted to the potential energy of alpha particle, because this alpha particle is in the field of nucleus. So the equation is kinetic energy of alpha particle from starting point equal to potential energy of alpha particle at the point of returning. So maximum kinetic energy is converted into maximum potential energy. So here you can write in the mathematical form Kinetic energy equal to potential energy 1 by 2 mv square, and this is the potential energy formula. So which is discussed in the 11th standard. So 1 upon 4 pi epsilon 0 Ze into 2e. What is Ze? Ze is charge on nucleus and 2e is the charge on alpha particle. So by substituting all the values, natural maximum kinetic energy of alpha particle is almost 7.7 mega electron volt. If you substitute all the values and find out D, it will be 3 into 10 raised to minus 14, that is 30 into 10 raised to minus 15 meter, and 30, it is a femtometer or Fermi. Femtometer 1F is equal to 10 raised to minus 15. So size of nucleus is less than 30 femtometer or 30 Fermi. Why this is less? How this is less? The alpha particle is here. From this point it returns, and here is the positively charged nucleus. It does not collide with the nucleus. So this nucleus has small radius or small size. This distance is 30 fm. So small size of nucleus should be less than 30 fm. It should be less than 30 fm. So this is the distance of approach. The formula for distance of approach is 2Ze square on 4 pi epsilon 0 into kinetic energy. You have to remember this formula and the relation between D and Z, D and kinetic energy. If kinetic energy is same for other atoms, then what is the distance of closest approach? If there is another element instead of gold and kinetic energy of alpha particle is same, suppose 7.7 mega electron volt, and there is another atom, the foil is made up of suppose aluminum, then Z is different, kinetic energy is same, then D will be directly proportional to Z. If Z is increased, D also increases. If the kinetic energy is less, then kinetic energy is less, then D is greater, because with low kinetic energy, the alpha particle, which is far from the atom of this element, so this D will be larger. If kinetic energy, suppose this is a gold and kinetic energy is less than this, kinetic energy is suppose 5 mega electron volt, then D is less, D is greater than 30 fm. This is greater than 30 fm. So in this way you can remember, distance of closest approach is directly proportional to Z, but here the condition is kinetic energy for all the material must be same. Then you can find the relation, and D is inversely proportional to kinetic energy. Now the next factor is impact parameter. Just we have seen D. What is the use of D? To determine size of nucleus, to estimate size of nucleus. Now impact parameter B. What is the impact parameter? Impact parameter estimates the deviation of alpha particle. The deviation of alpha particle. If suppose alpha particles are incident on the atom, then Consider this alpha particle is incident normally on the atom. It returns back. It returns back. So here B is 0. What is B? B is normal distance. It is normal distance. Normal distance or perpendicular distance. Perpendicular distance. The definition is not asked in exam, competitive exams. Normal distance or perpendicular distance between velocity, direction of velocity, and center of nucleus. Center of nucleus. Suppose if you take this alpha particle, then direction of velocities and distance between direction of velocity is like this. So it is passing through the center. Direction of velocity is passing through the center of nucleus. So here B is equal to 0. Direction of velocity or path of alpha particle, you can say like this also. Path of alpha particle. Path of alpha particle. So this is the path and the center of nucleus. So here B is equal to 0. Then the deviation is to 180 degree. If you consider this alpha particle, then here the distance B is not equal to 0. This is the impact parameter. If you consider this alpha particle, this B is very large. So there is no deviation. So there is no effect of B, that is impact parameter, on this alpha particle. So this B determines the deviation, and B can be obtained by using this formula. ZE square cot theta by 2 upon 4 pi epsilon 0 kinetic energy. So this is the formula. So multiple choice from this point of impact parameter that we will discuss in the next video. One more factor, the number of alpha particles scattered through an angle theta is given by n equal to z square divided by sine raised to 4 theta by 2 is sine of theta by 2 sine raised to 4 kinetic energy. So this is the formula for alpha particles scattered. So these 3 points are NCERT points which are required for NEET exam. So we will discuss in the next video some MCQs regarding with these 3 points. So here is the end of spectral lines in hydrogen spectrum. Now in the next video we will also discuss what are the limitations of Bohr postulate, and one postulate is overcome, limitation of one postulate is overcome, drawback of Bohr postulate is overcome by another scientist, de Broglie, and de Broglie explanation.